In this last section of Unit 7, Lesson 3, we are going to solve for x, but we're not going to use a calculator. So I'm going to start by writing this in exponential form. The base is 3, raised to the value on the opposite side of the equal sign, equals 2x. Now I need to figure out what is 3 to the 5th. Well, 3 times 3 is 9, so another 3 times 3 is 9, and then we have one additional 3. There's 5 threes. 9 times 9 is 81. 81 times 3 is 243. Dividing by 2, 243 divided by 2. I can leave it in that form. What I need you to recognize is this. The base here will always be a value that's greater than 0. I'm going to say this again, and you should have this in your notes. The base will always be a value that's greater than 0. The value behind the base, so we call the answer position, this is like the base, the exponent, and the answer when we rewrite it in exponential form. This value will always be greater than 0. These two values will always be greater than 0. Okay, keeping that in mind. Let's go on right now to the next one. Writing this in exponential form to solve. I start with the base, raised to the value on the opposite side of the equal sign, equals x. 7 squared is 49. Now what we're going to want to get in the habit of doing is that we're going to want to get in the habit of plugging it back in to make sure it works. So when I plug this back in, this value must be greater than 0. Please watch. If I take 2 times 243 divided by 2, so just so you can see this, if you're a visual learner like myself, log base 3, and I'm going to take 2 times what I was able to achieve for an answer for x. Let's see, well, the 2 divided by 2 will simplify to 1, and then 3 to the 5th is 243. I agree with this answer. Over here, if I plug it in, 7 squared is 49. I agree with this answer. We're moving on to the third example. 8 raised to the x equals 1. When we take a value and raise it to the 0 power, we end up with 1. Moving down to a little more complex problems. Whenever we have it in this form, and what I mean by this is we have a log base of value and an answer behind, a log base of value and an answer behind. What I do not want it to look like, and I'm just going to adjust this. Notice that here we have a plus or minus behind that. It cannot be in that form. So you can't have an additional plus or minus behind either the left or the right side. But when the log and the base are exactly the same on the left and the right, what we get to do is we get to actually eliminate the log base 3 in this case. Now it could have been a log base 5, a log base 7, log base 1, whatever. And now we have x equals 7. And that's true. If I would make this a 7, the left side and the right side would be equal. Example number 5 from this portion, we're going to rewrite an exponential position. So we have 4 raised to x equals 1/2. This is tricky. This is tricky if this is your first day being introduced to logs. So I need to find out, what do I need to raise 4 to get to 1/2? Well, I know that the square root of 4 equals 2, so keep that in mind. I also know that the nth root on a square root is a 2, so I could rewrite this as 4 to the 1/2 equals 2. Whenever we see a value raised to the power of 1/2, it's the same as taking the square root. So yes, 4 to the 1/2 equals 2, but notice how the 2 is not on top. So if I said this was the answer, that's what I would achieve, but I don't want the 2 to be on top. The 2 has to say, hey, I'm not happy. I need to go to the bottom. So if we take the exponent on the 2 that is currently a hidden 1 and we make it a -1, then it would bring it to the bottom. What I need to do is then make the x equal to -1/2. I'm going to write that out right now. If I have it, I have a little space up here. If I have 4 raised to the -1/2, I'm able to achieve positive 1/2. Why is that? Because simply 4 to the 1/2 is 2, and now applying that negative sign, which I have not applied, said, hey, 2's not happy, and it comes down to the bottom. I'm going to have us go back at the very end of this video, and you're going to try one similar to this. Next up, 8 raised to the x equals 8, and we know in order for these to be equal, x would have to be 1. Moving on to the next one. Okay, so we have log base 5 and log base 5. Remember when I showed you up here, I said, hey, we can't have a plus or minus in back. That's true unless it's included in parentheses like I see right here. So up here we had log base 3 and log base 3, and we were able to cancel them out. Here we're also able to cancel out log base 5s and log base 5s, and we have 2x minus 1 equals 23. And then we're simply going to solve. So 2x equals 24. Dividing by 2, I have x equals 12. And then I need to make sure it's not going to be an answer that we did all the math right. It's called an extraneous solution. But when I plug it in, I end up with a value here that's not greater than 0. So let's check. 2 times 12 is 24. 24 minus 1 is 23. That looks good. Let's come over here. This is something that's different in this particular example. So what we're going to do here is we're going to take this exponent. So if there's ever an exponent on the answer position, we can rewrite it by always putting it in front. So it's going to be 2 times, and then I have log base 8 of 8 equals x. Why would we do that? Because just like up here, we were able to see that log base 8 of 8 is 1, the same thing is true too. So when we do the mental math here, we're asking ourselves, 8 raised to what power equals 8? 8 raised to the first power equals 8. So this part evaluated is 1. We could take it times the 2 up front, and we end up with x equals 2. Difficult one. Moving on to our last row before I have you try a few like this. Last row here. Give me 1 second to adjust this paper. Oh, okay, here we go. So when I rewrite this, whenever I see that ln, that stands for natural log, I'm going to rewrite it in equivalent form, which is log base e. And then I'm going to rewrite it in exponential form. So the base is the number e. Remember, e is no longer in our mind thought of as a variable. So base raised to the opposite side equals 1. The only number you can take a value to and raise it to this, the only number you can raise a value to and get 1 is 0. So x equals 0. E to the 0 is 1. Likewise, with the next example, I'm going to rewrite the natural log as log base e of e raised to the 7 equals x. This example is going to mirror this example. And what do I mean by that? Whenever we have the log and these two values are the same, we're always able to take whatever this exponent is. In fact, these don't even have to be the same. It's just making it easier for this particular example. Whenever you have an exponent in the answer position, we can always throw it in front. So I'm going to throw the 7 in front. Log base e of e equals x. Is it necessary to show all of this work for your homework? Absolutely, to receive any credit for doing it. We're doing mental math. E raised to what value equals e? When they're exactly the same, this portion will always be 1. So I have 1 times 7 equals x. 7 times 1 is 7. Okay, moving on here to our last one before I have you try a few. I'm going to rewrite the ln in its equivalent form, log base e. And now we can see, just like this example up here, I have log base e and log base e. There's no additional plus or minus, so I'm able to eliminate these or simplify them. We have 3x equals 27, so x equals 9. And when we plug it in, 3 times 9 is 27. That is working. We do this problem that students were asked to try in class. Well, I'm going to rewrite it right now in exponential position. So 3 raised to the what equals 1 over 81. The first thing I'm thinking is, what do I have to raise 3 to get to 81? So I'm going to do some work. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So it takes 4 3's multiplied together to get to 81. But notice that the 81 is not on top. If this was the problem, I would say x equals 4 and problem is done. But it's not that way. The 81 is on the bottom, which means I need this exponent to be negative. So instead of being a positive 4, the answer is negative 4. And for many of us, it works best to actually then write this down. So I took this statement and I put in a negative 4. Let's make sure that works. So 3 to the 4th is 81, but then this says it's not happy. It goes to the bottom, and we can see the left side equals the right side. I just proved to myself that, in fact, the answer is negative 4. A complex problem. Let's see if I set this up right. We have a base of 1 over 32. And we're going to raise it to the 1/5 power, and it equals x. So we need to apply that 1/5 to both the top and the bottom. So we're going to apply it to the 1, and I'm going to apply it to the 32 on the bottom. What does this mean? This is important, okay? This means we're going to take and we're going to ask ourselves, we always start with the bottom number first. What times itself 5 times equals 1? And the answer is? What number times itself 5 times equals 1? 1. So I've done the bottom number, and I achieve an answer of 1, and then I take it to the first power. You do the top number, or the numerator second. 1 to the first is 1. So this equals 1. We're going to do the same concept down below. So we're taking and asking ourselves, what times itself 5 times equals 32? 2 times 2 times 2 times 2 times 2. You're right, I got to check. 2 times 2 is 4, 8, 16, 32. Okay, that's 2. And then I'm going to raise it to the first power, just like I did here. And 2 to the first is 2. The correct answer for x is 1/2.